Welcome back all participants for the second part of this session, and welcome ma'am again. You can continue this.
Thank you.
Thank you.
Right. So we start with a glimpse of history of cryptography. Reading about a new topic, a new thing, a new technology, anything without getting to know the history of it won't be doing justice to that thing. So we should always know the history. Like I started this presentation. So like I started this presentation with the motivation why we chose cryptography, right? So before we go to the classical cryptography and modern cryptography, we should really know about the history of cryptography, right? So Enigma. So one of us wrote in the chat box that yes, he has watched a movie about Enigma, World War II. Right? We have a movie on World War II, Enigma. And many of us have not seen it. So I hope we'll see it now. Right? So, in World War II, Enigma was the first encryption machine used. In the field of cryptography, this was the first invented machine that was used to exchange messages in secret form, and Germans used that machine. Trust me, if there would not have been Enigma machine in World War II, the fate of this World War II and the world would have been different. So Enigma played a significant role in World War II, because Germans were the first to use some encryption machines, so they were a step ahead. Before World War II broke out in 1939, the Germans had planned a special way of keeping their communication secret. The Army, Navy, and the Air Force were told to encode their messages using cipher machines, Enigma. So let's have a look about it.
On August 5th, 1857, a 4,300-kilometer-long cable was laid across the Atlantic Ocean. It provided a link between Britain and the Americas, further strengthening their social and economic alliances. Now, information could be represented as a pattern of electrical pulses and sent across the world almost instantaneously. Stock tickers and money transfers, these were commercial applications invented by Western Union, which ushered in a new era of global communication.
Stand by for this announcement. Germany has invaded Poland and has bombed many towns. General mobilization has been ordered in Britain and France.
And consequently, this country is at war with Germany.
The world, which is the real cause of the war that today threatens the freedom of mankind.
È già stata consegnata agli
The Japanese have attacked Pearl Harbor, Hawaii by air, President Roosevelt has just announced.
During World War II, Germany, Italy, and Japan were far outnumbered by the Allies. Their only conceivable path to victory was the ability to launch widespread surprise attacks. So the goal of encryption technology was to automate the one-time pad using an encryption machine. Ideally, this machine would accept an input letter, apply a random shift, and output the encrypted letter. However, all machines follow the same principle. They begin in some initial configuration known as a state. They accept some input. They do an operation with the input, and then they produce an output. The operation from initial state to final state is always predictable and repeatable. So the goal was to produce identical machines that output a scrambled sequence of shifts, which took a long time to repeat. Therefore, Alice and Bob could generate an identical shift sequence as follows. First, they need to share identical machines and agree on an initial position, which is defined as the key setting. Then they align their machines to the same position, and finally cycle through the identical operations to achieve identical sequences. Now, the state-of-the-art technology at the time was called a rotor encryption machine. We are all familiar with the mechanical process of an odometer, which takes a long time to finally repeat its cycle. Now imagine we scramble the numbers on the wheels of the odometer. When it ticks forward, a new shift could be generated by adding up each number on the rotors. This is the rough idea behind rotor encryption machines. For example, the message "attack northwest" would be encrypted as follows. Notice how a new shift is used at each position in the message. With 3 rotors, each with 26 numbers, the length of the sequence before repeating is 26 times 26 times 26. This is equivalent to having a list of shifts 17,576 numbers long. Understand that each rotor position is equivalent to a location in this sequence. The initial machine state is known as the key setting, and the collection of all possible key settings defines the key space. This key space increases if the number of ways to initially configure the machine increases. For example, if the rotors can be rearranged, then the order can be selected in 6 ways. Let's visualize the key space at this point. First, we choose from one of 6 possible rotor orderings. Then we select an initial position from the rotor sequence. This gives us a key space with over 100,000 key settings. Remember, every machine configuration is a point in this space. When we select a key setting, we are selecting a starting point in this space, which then determines the rest of the shift sequence. Give away the key setting, and you give away the entire sequence. The security of rotor machines depends on both the size of this key space and the randomness of the key setting. During World War II, one of the most important encryption technologies used by the German military was known as the Enigma. It was an electromechanical rotor machine invented by a German engineer at the end of World War I. Each rotor wheel had electrical contacts on either side with a maze of wirings within. So at each rotor position, there was an electrical path from every input letter to every output letter. When the rotor advanced, an entirely new path was defined for each letter. During the war, they continually tried to increase the key space of the Enigma in order to make it stronger. For example, some changes they made were to add a 4th rotor wheel and increase the number of possible rotors you could put into the machine to 60. This had the effect of massively increasing the key space. Near the end of the war, the Enigma could be set up in over 150 million ways. Guessing the key setting, which was used for a given message, was about as likely as guessing the outcome of 26 dice rolls. This gave the Germans confidence that the Allies, even if they had a copy of the Enigma, could never check all possible key settings. For two parties to communicate using the Enigma, it required that they first share the daily key settings. This allowed them to align their machines to the same position. This protocol changed over and over during the war, but generally involved distributing key sheets in advance to all operators. Each day, the operator would cut off the daily settings, and this would tell them the daily configuration of their machine, such as what rotors to use and the order of the rotors. This key setting was then to be destroyed after use. However, one vital step was left to the operator. They were to select a random initial position of each rotor before communication began. And a very simple mistake was made by some fatigued operators. We make this exact same mistake every time we set a bike lock combination because we tend to rotate the cylinders only a few clicks from the initial state, or we reuse a common password. This destroyed the uniform distribution of the initial rotor position, and after repeated observations, it allowed the Allies to reverse engineer the rotor wirings completely. The second major error was a design error, not a procedural one. The Enigma was designed so that an input letter would never encrypt to itself. So given an encrypted letter such as L, you can now eliminate the possibility that L was the original letter. What they thought was a strength was actually a weakness in design. And this led to a code-breaking machine initially designed by the Poles and later improved by the British-American effort. The bomb was multiple Enigma rotors chained together, allowing it to rapidly test different key settings. It took advantage of the fact that common words were known to be in the original message, such as weather, and these came to be known as cribs. For a given message in crib, the bomb could scan through all possible rotor positions and orders in order to find possible key settings in a matter of minutes. This machine allowed the Allies to read German commands within hours of them being issued. It was a fatal blow to their combat strategy as the Allies could anticipate their next move. One fact remains. This initial attempt at automating the one-time pad failed. If the operators had instead rolled dice to decide their initial rotor positions, the starting point in the sequence could have been uniformly distributed. This would have prevented the reverse engineering of the rotor wirings, and if the Enigma allowed letters to be encrypted to themselves, the bomb could not have taken advantage of cribs. And this would have required the Allies to check the entire key space, which was impossible even with the fastest computer. Repetition reduced the key space. Otherwise, the outcome of World War II could have been drastically different.
So I hope you enjoyed that video. At least once a day, the Germans changed the order of the rotors. I tell you the simple concept behind the Enigma machine. You know, I want to send, let's do bombardment at position X. So what we do, L will be encrypted as some other letter chosen from A to Z, right? If it would have been a fixed letter, then that cipher would be called something else. But every time A would be chosen as some other letter. So this kind of encryption is called using one-time pad, right? You encrypt A as X one time, other time you use A as L. And the third time when you encrypt A, you encrypt A as U. So this one-time pad gives you possibility of choosing A as a rest of the letters other than A, right? Or maybe if A as well, then all letters A to Z, right? So choosing one-time pad will never allow the hacker to guess that every time A would be chosen as L. No, because the next time A would be chosen as something else, right? So electrically, how it happens, you press the button for A, what is typed, written will be L. Next time you press A, it will be typed as U, right? So these are the wire settings. And initially, two similar machines are exchanged, are kept with transmitter and receiver, and the initial position is decided. And later, using that sequence of one-time pad, these two communicate, right? But this video also discussed about the limitations of such machine. Like A would never be encrypted as A. That was one of the limitations which they thought was the strength. Another mistake what was done, the initial password was always close to what the previous password was. The thing we do in our bikes. If my code is 999, every time I shift 9 by 8 or 7, 1 or 2 place, right? That is what a human tendency is. So that came out to be another limitation. So with reverse engineering, hackers broke it. At least once a day, how we keep our algorithm secret. We choose a key, transmitter and receiver exchange that key in case of secret key cryptography. And do we use the same key for 6 months, 1 year, 2 years, 5 years, 10 years in a row? No. Every now and then, the keys are altered. This was an interview question asked to me when I appeared for some assistant professor job in a teaching university in an organization. They asked me that your specialization is cryptography. So tell me one thing. You and I share some secret message with the help of a key. You are a military person. I am a military person. We use a fixed algorithm and we are using a key. So for how long can you keep that system secret, that system strong? And the answer to it was every 2 months or 3 months, the key was changed. So if a hacker takes 5 days, 10 days, 10 days, 15 days to break that key, maybe before that, we change the key. Isn't it great? Right? So it's not always the machines, but a combination of machine and human mind and intuition that works well in coming up with a good, secure system. Right? At least once a day, the Germans change the order of the rotors, the starting positions, and the plug board connections to decipher a message sent using Enigma. You had to work exactly how all of these had been sent. In 1930s, Polish cipher experts secretly began to try to crack the code. So Germans made the Enigma machine, but Polish people, they try hacking it. Just before war broke out, they managed to pass models and drawings of Enigma to British and French code breakers. Later, Enigma was broken. So Germans were initially very confident, but Polish people, they broke it and they made allies with British and French. And the thing which was strength of Germans was taken away. What happened in Japan? A US army group, the SS, managed to break the highest security Japanese diplomatic cipher system. It was called as Purple. Like Germans developed Enigma, Japanese people, they developed Purple. This was by Americans in 1940, before World War II began. Japanese Navy and Army largely used code book systems, later with a separate numerical additive. So these are the ways they use. So Enigma, Purple, these are some machines, those were used in World War. Allies, what did Allies do? Allied cipher machines used in World War II included British Type X and the American SIGABA, SIGABA. So there were different machines proposed by different countries. So British, they had Type X, Americans, they had SIGABA. Both were electromechanical rotor designs. Rotor design, I said, you physically press a button A, what you get is maybe 3, right? Or for pressing A, you get U or L, right? Because inside there is wiring like a switching circuit. Both were electromechanical rotors designed similar in spirit to Enigma, albeit with major improvements. So, and these were like improved version of Enigma, because Enigma was the first introduced machine and it had some limitations. Those were overcome in next machines. Neither is known to have been broken by anyone during the war. Later it got broken, but during the war, it really helped. So this was about history. Now let's talk about, if I really want to classify cryptography in today's world, we have symmetric key cryptography. Symmetric key cryptography. We have asymmetric key cryptography. This is also called as classical cryptography. Asymmetric, this is called modern cryptography. In classical cryptography, if you really want to remember this, it will have a secret key. A and B should exchange key before actual transmission of message. Here in asymmetric key cryptography, we have pair of keys that we eliminate the use of exchange of keys. That is public and private keys. We have pair of keys and there is no need for sharing the secret key between the transmitter and receiver. This is a modern concept. So these are few examples of classical cryptography, that is transposition and substitution cipher. And these are the modern examples of modern cryptography: stream cipher and block cipher. So to remember, classical cryptography has a secret key. Modern cryptography, symmetric is classified as classical and modern cryptography. Sorry. And asymmetric will have always pair of keys. In your secret key, we have classical and modern both, right? Let's see. If I take example of classical cryptography, substitution cipher and transposition cipher are examples. You should be knowing this, right? Replaces the characters in the substitution letter or groups of letters that are systematically replaced throughout the message for other letters. Example for substitution is Caesar, monoalphabetic, Playfair, polyalphabetic, Varnam. These are some examples, the names you should be knowing with. What happens here? Systematically replaced through message, like A will be replaced every time with D. A will be shifted to B, C, D, 3 positions. B will be shifted to 3 positions, C, D, E. So B will be replaced as D. So there is a fixed sequence of shift. Those are your substitution cipher. In transposition cipher, the letters themselves are kept unchanged, but their order with the message is scrambled. You write, hello, my name is Nilufal. Individual letter is scrambled in the sentence. Are you getting? In substitution cipher, the letter will be replaced by some other letter. In transposition, so if there is a complete sentence, hi, my name is Nilufal, maybe H will be replaced with some other letter. But here in transposition cipher, H will be H, but in complete sentence, the order of the letters will be scrambled. Am I clear? Is that clear with you all? I hope so. Are we all into this? Are we into this? I hope I'm not running too fast and you are with me, all of you. Thank you, Sarah. I have got one response. Thank you. Okay. So it's simple. In this, if I exchange a sentence, every letter will be replaced by some other letter. Here, letters, all the letters remain same, only their order will be changed. Caesar cipher is the earliest known substitution cipher. You might have heard about Julius Caesar. He used it. It was first attested used in military affairs. It replaces each letter by third letter. Example, meet me after the toga party. This is the message A wants to send to B. So, if we remember the order of English alphabets, every letter is replaced by third letter. So, M, N, O, P. M will shift to 1, 2, 3 position. So M will be encoded as P. E will be encoded as, every letter shifts to 3 position. E, F. E will be encoded as E, F, G. Sorry, my hands are a little sticky. E, F, G, H. Just a moment. E, F, G, H. So 1, 2, 3, third position. So M is P, E is H, T is T, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W. 3 positions. M is P, E is H. A will be B, C, D, 3 positions. F will be G, H, I, 3 positions. T will be W. E will be H, R, S, T, U, 3 positions. T will be W, H will be I, J, K, L, M, N, O, P, Q, R, A, B, C, D, E, F, G, H, I, J, K, third position. E will be H. T will be W. O, P, Q, R. O, P, Q, R, third position. Right? So, in Caesar cipher, what happens? Every letter is encrypted with 3 position next shift. So what will be Z encrypted as? I'm looking for responses in the chat box. Z will be encrypted as? That's a question, right? I got one response. I'll not open up. I'm looking for more responses. Okay, I got one response, D. This is shifting 1 position. This is shifting 2 position. And this is shifting 3 position. And this is shifting 4 positions. In Caesar cipher, we shift by 3 positions. I'm looking for some more responses. Yes. When alphabets finishes at Z, we restart from A. So Z will be encrypted as, I believe it should be encrypted as C. Tell me if I'm wrong. Should it be encrypted as C or D? Okay, I got one response. What do other participants think? Should be C, right? I think it should be C. A should be encrypted as B. A should be encrypted as D. Z should change to C, right? B should be encrypted as C, D, E. C should be encrypted as D, E, F. D should be encrypted as D, E, F, G. Am I correct? So when you write A to Z, and you can do that like. So let's encrypt. Hi, my name is X. So let's encrypt it with Caesar cipher. I want the response in the chat box. Everyone, please. I tell you the golden rule. Every letter gets shifted by 3 positions. A, if you have pen and paper, I'm solving it. See? Okay, it's white, so in this background it's not visible. Anyway, I am waiting for responses. Hi, my name is X. Using Caesar cipher, please, yes. Please take your time. The hint is every letter should be shifted to 3 jumps. There you can see M. Sorry. M got changed to P. How? First jump N, second jump O, third jump P. So M should be encrypted as P. Likewise, H should be encrypted as H I J K. H is K. You should write like beneath H. You write I J K L. Correct. LV or LU? N-O-P. I-Z-A-P. C-G-M-N-O-P. E-F-G-H. J-K-L-S. Q-R-S-T-U-V. So as per me, it should be K-L-P-B-Q-D-P-H-L-V. L-V-A. Correct? Yes, Sarah corrected. Varun also. Miomi, right? Miomi. Tushari, correct. Amit, correct. Chaman, correct. Mohan. Mohan, I'm waiting for your response. Shift the letters to 3 places. Mohan also responded, right? Correct. APT, right? So I hope next time you talk to your friend that I am using Caesar cipher and you can exchange your encrypted message like this. Try doing it. It's fun, right? In transposition cipher. So that was about Caesar cipher. What is it about transposition cipher? In transposition cipher, mapping is performed by some sort of permutation on the plain text letters. Meet me after the toga party. See, rail fence of depth 2. What happens here? ME. In rail fence, what happens? We are, jumbling. You're scrambling the position. Depth of 2. So here, see, we are, scrambling them. These are the total letters, and how we are doing it. Every, second letter we are picking up. M, then E, then again M, then A, then T, then R. After R, H, then T. Are we following it? After T, G, then P, then R, then Y. Right? And what are we left with? The next time we are picking up the second letter. Initially we were picking up third letters. First, third, fifth, seventh, ninth. Now what we are doing? Second, E, fourth, T, sixth, E, eighth, letter F, 10th, E, 12th, T, 14th, E, 16th, O, 18th, A, 20th, A, and 22nd, T. And when I write it in sequence, M, E, M, A, T, R, H, T, G, R, Y, right? All these are scrambled to a depth of 2. So even in rail fence, there has to be a rule. And what your transmitter and receiver agrees on, they are shifting it, scrambling the complete sentence with a depth of 2. Is that clear? Should we try something on rail fence? Should we try something on rail fence? Hi, my name is X. Should we try? Or you're tired, bored? Or you understood? Let's move further. How they separate words then. There is a rule for that. Even after this, they send a sequence of, 2, like 4, 2, 5, 3, like that also they send, right? And there could be, scrambling of that as well. 4, 2, 4, 3, 4, 5. And they can even scramble them by depth of 2. So this is followed by the number of letters each word must have, right? A lot of thinking can be involved here. And you can add one more step to it. That's up to you. So these are the famous ones in their classical time when they evolved. This is relative frequency of letters in English text. If you observe, read a paragraph, like I ask you to write an essay on summers. Summers are good time to enjoy. Summers have this temperatures, flowers bloom, and all like that. If you study a complete paragraph or so, there is a tendency of few letters which comes so many times. E comes so many times whenever you write something in English. A comes so many times. E has maximum tendency of appearing. A also comes so many times. T also comes so many times. This makes total 100, right? This percentage. 12 plus 8, 20, like that. This is total, So this is relative frequency of letters in English text. Z appears so much less. J appears, just try out any sentence. You'll see You are using E, A, T, O, N, I, H so many times, but you are hardly using letters like J, Q, Z, right? So this is experimentally found that these are the relative frequency of letters in English text. Now let's come to modern cryptography. So we have like old people, they used to use scissor cipher, transposition cipher, rail fence. Now what we do, modern people, what do they do? They use secret key cryptography and public key cryptography. The secret key cryptography is also called as symmetric key cryptography, and public key cryptography is also called as asymmetric. This secret is symmetric, public is asymmetric, asymmetric and symmetric. It uses a single key for both encryption and decryption. The same key used for encryption that is used for decryption, like the example of exclusive XOR I have taken. With the same key you XOR, you get encrypted data. The encrypted data you XOR, you get decrypted data. Like, let me write. This is plain text or message. Plain text when encrypted, this is bracket, right? Encryption of plain text gives you ciphertext, right? When you decrypt your ciphertext, what do you get? You get your plain text. So this you can write as decryption of, what is C? C is E bracket of P. And the simple things, they just look complex. See, I'm making a simple thing look complex in front of your eyes. Making a simple thing look complex. What should be the answer? See, bracket means a function. P encrypted makes C. Encryption of plain text makes ciphertext. Decryption of ciphertext makes plain text. Now, decryption of encryption of plain text, what does it make? Makes sense? Right. Thank you, Mohan and Sarah. So this is plain text. What is bracket of C? Bracket of C. What is C? Inside bracket, I can write E of P. As simple as that. Right? So here, what is important is key, right? So if it is a private key cryptography or secret key cryptography or symmetric key cryptography, we use a single key for encryption and decryption. Here, what do we use? We have to use a key, and this is the very same key that we have used at encryption, right? So you can see here, I'm using the very same key for encryption. So encrypting the plain text will make a ciphertext, and using the same key while decrypting the ciphertext will give you the plain text, right? And when I apply decryption and encryption, both functions to plain text. So first inside function, that is encryption of plain text, will give you ciphertext, and decryption of that ciphertext will give you the plain text, right? So public key cryptography, we use one key for encryption, but this is something different. We use a pair of keys, one for encryption, another for decryption. How is that possible? We'll see. Also called as asymmetric encryption. So these are used for authentication, non-repudiation, and key exchange. Hash functions are also a kind of cryptography. Here we use mathematical transform to irreversibly encrypt information message. Here, once one thing is encrypted, you cannot decrypt it. But where do we use it? In providing digital fingerprinting. My fingerprinting will be encrypted as a fixed kind of data, and that cannot be reversed. So using key in that there the key is called as hash function. This role of this bracket is providing functioning to it, right? So that is called as hash function. Irreversible. Here that ciphertext will not be able to be decrypted back. That is the job of the hash functions. Now I don't want to read that message, but I have a reference. Like my signature should match this signature. There we use hash functions. Are you getting a little idea of it? As we progress more, we study hash functions in detail, it will be more clear. So there are certain things there we do not want to decrypt the message. I just need to check it with the reference, match it with the reference. Like bank checks and all, you sign, bank has a reference copy of your signature. They match it with the reference every time. So hashing is like that. Plain text, with the help of key, we get ciphertext. With the help of same key, we get plain text back. This is secret key or symmetric key encryption. Use a single key. Now here, see the color in asymmetric cryptography. We are using two different colors of keys, pink and blue. One is used for encryption, plain text to ciphertext. Another is used for decryption, ciphertext to plain text. And if we are using a hash function instead of a normal key, we always get plain text to ciphertext, and there is no reverse back, no reverse going. Hash function, that is why it is also called as one-way cryptographic function. It has no key since the plain text is not recoverable from the ciphertext, right? Symmetric and asymmetric cryptosystem. A symmetric cryptosystem consists of an encryption algorithm, a decryption algorithm, and some secure private keys at minimum. Yahi hota hai? This is what we have in symmetric. And symmetric cryptosystems uses the same key for encryption and decryption. These two are very famous example. AES I mentioned in the last session before the break. DES, this was one of the very famous algorithm. When AES came, it replaced DES. So I hope you have heard about both. If not, you have heard about AES because this is the most popular one these days. Asymmetric cryptosystem or public key cryptosystem. These are the cryptosystems where the encryption key differs from the decryption key. And one of the famous example of such system is RSA. Right? RSA is very famous crypto system. In a very famous example of asymmetric. Cryptographic algorithms, if I want to classify, see, I have block ciphers, stream ciphers, hashes. These are the major classification. How many types of algorithm I have? See, simple Zoring was an example, a very vague, simple example. Basically, we have block ciphers, we have stream ciphers, we have hashes, we have Diffie-Hellman key exchange methods. This is method for sharing keys. RSA is a public key encryption and digital signature. Algamal digital signature methods for authentication. So this is the classification. I think you should keep a note of it. So these are the various type of cryptographic algorithms, famous ones. Now block ciphers, within block cipher is a category. We have different examples for it. DES, AES are examples of it. right? So let's move further. Block ciphers processes messages into blocks. Like if I say, hello, my name is Nilufal, if I convert it into bits, I might get 1000 bits. So what it will do, block cipher, every time it might take 64 bits of data at once and encrypt it. Or maybe it will take, 128 bit at once. Or maybe it will take 256. I mean, it should be, it should be some value 2 to the power n. Integer multiple of 2. Like a substitution on very big character, 64 bit or more at once. But what are stream ciphers? 1 by 1 bit encryption occurs. One thing, you pick 64 bit at once, convert it into encrypted. Another thing, 1 by 1, serially data goes for encryption. So stream ciphers. But most of the research and so much of data is available for block ciphers. Block ciphers are more preferred ones because it even saves time. No, at once you are encrypting 64 bits. In stream ciphers, you're encrypting bit by bit, right? Now, what are S boxes, P boxes? Just so sorry for the inconvenience. So we were talking about block ciphers and stream ciphers. So if I talk about block ciphers, the security of block ciphers lies within two more things. In block ciphers, we use some S boxes within and P boxes. You remember in the chat box, I once discussed how an algorithm works. An algorithm works with several steps like this. You can see this. Maybe the first thing is XORing with the key, second thing is left shifting, third thing is divide into 64, 32, 32 bits. I have taken example of block cipher considering 64 bit at once. So 32, 32 divide, then right shift, then XOR. Maybe there is a step introduced in between passing through S box and passing through P box. What are these steps? So these are steps, right? Now, what is a S box? S box is a substitution box. Suppose you you have an inbuilt S box. There you have all combinations. If you take 4 bit at once, like I give you an example. If you take 2 bit at once, how many possible combinations you can make? 2 bit at once, 2 to the power n is the formula, right? You can make 4 combinations at once. How? With the help of 2 bits, how many combinations you can make? You can make 0, 0. You can make 0, 1. You can make 1, 0. And you can make 1, 1. Let me see. 0, 0, 0, 1, 1, 0, 1, 1. Correct. These are the 4 possible combinations, right? So in S boxes, maybe that is a box where for every 2 bits it gets substituted every time. Maybe 0, 0 will come out as 0, 1. Maybe 0, 1 will come out as 1, 1. Maybe 1, 0 will come out as 0, 0. And maybe 1, 1 will come out as 1, 0. Then that means when you pass some bits through S box, that will substitute the bits into some other bits. So this creates confusion and diffusion. In permutation box also, position of bits get shifted. So aren't these similar in providing secrecy and security. This is similar to these steps, right? You do right shift, or you do substitute, you do XOR, or you shift their position, right? So most of the block ciphers, they use S boxes and P boxes within their algorithm steps. So S boxes are invertible lookup tables that depends on keys. P boxes, we reorder bits, right? Key schedule, and in every step, like I said, no, in the chat box I've discussed. And next time you use key, maybe you don't use this in the next round, you don't use the same key. Maybe you use some left shift your key with 2 position, and this is used in the next round. And in the third round, this new key is again shifted to position, which is used in the third round. And third round key is again shifted to 2 positions left side and used in the fourth round. Are you getting? So key scheduling, passing through S box, passing through P box, these are some basic features of a block cipher. So these are the things, if you study block ciphers in detail, you'll get a detailed knowledge of this. So this is just to give you a hint of what happens. Like key passes, your message passes through S box, then it passes through P box, then one round complete. In second round, different key, then again it passes S box, then it passes in third round, or maybe in between some XORing, some shifting. That depends on what is the rule of your algorithm, right? These are the basic things. I hope you're getting. DES is one of the very famous block cipher. DES is a 64-bit. Here it uses data of 64 bits every time, and it uses key of 56 bits every time. It uses 16 rounds. See, block cipher encrypt 64 bit at once. Key it uses 56 bits. It uses 16 round structure, 16 rounds. It was designed by NSA and IBM in 1976. Yes, when I was talking about NIST, one of you answered me NSA. It was initially NSA, now it is NIST. Right, in 1976. It worked well for 20 years. There was no substitute of DES. Everyone used to rely on DES for all kind of encryption. But you know, with the evolution of supercomputers and all, we start breaking codes. Have I mentioned the term brute force attack? Yes, that's the chat box, sorry. No, I have not mentioned it. Brute force attack. What is it? Let me explain. One thing I just discussed, if I give you 2 bits, how many possible combinations you get? 2 to the power n, 4 combinations. If I give you 4 bits, how many combinations if I give you 3 bits, how many combinations you get? 8. How 8? 000, 001, 010, 011. Likewise, you can make 8 combinations. And if I give you small n equals to 4, how many combinations? You can make 16 combinations because 2 to the power 4. Correct, right? So, if suppose I use a 2-bit key, now hack 2 bits key, hacker has to try out how many possible combinations. That key could be possibly 00 or 01 or 10 or 11. How many possibility that key would be of? There is a possibility that key could be either 00, right, or 01 or 10 or 11. There is no 5th possibility. So isn't it easy to guess by several hit and trials and all? Because in every message, the first word is hello, the last word is bye or take care. So we do somehow encrypt with reverse engineering. Now suppose key is of 3 bits. The hacker has to try 8 possible combinations. If the key is of 4 bits, hacker has to try 16 possible combinations. Now, if the key is 64 bits, now in DES it is 56, no? 56 bits. How many? So in above mentioned cases, the hacker can possibly try by hit and trial 2 combinations, 3 combinations, 2 combinations, 8 combinations, 4 combinations, 8 combinations, 16 combinations. But now if the bit is 56, if the key is 56 bits key, how many possible combinations? How many possible combinations? Please use calculator and tell me. I'm waiting for the responses. I'm waiting for the responses. If key is of 56 bits, how many possible combinations of key can be made? Correct. 72057. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 digit combination. These many combinations of keys. Can a hacker try each one in every trial? If he tries one by one all combinations, even with the help of the computers that we use these days, it would take years to break that code. Do you agree? Maybe with the help of supercomputers, in few days. Back in time in 1976, trying out these many combinations were so difficult. And I mentioned the term brute force attack. Brute force attack means trying all possible combinations. Yes, it could not be broken if we manually do it, or if with the help of our simple computers. But yes, these days we have supercomputers. They try these many combinations very fast. So in 1976, using DES and a 56-bit key length was a good enough security. But in 1998, the DES was made obsolete, because in these 20 years, we came up with supercomputers and evolution, and there are hackers. They have different hardware machines and hit and trial combinations and some software. So they could try out these many combinations in a few days, and this DES was broken in 15-20 days. I mean, if you with the help of brute force attack also, it can be broken in few days. So that is brute force attack, trying out every possible combination, right? So this is the website also I have provided, how DES was evolved. It was in collaboration with IBM, so you can read that. If you want to go into detail of this, I don't know if everybody will be interested, but just quickly I'll give you. 64 bits is divided into 32 left, 32 right. It is XORed with key first, then it is shuffled, it passes through its box, it is XORed again with key, then it is expanded 48 bit again into 32 bits into 48, then XORed, then expanded, then the second round starts. So you know how I started. When I started studying DES, I have taken it as my master's thesis in like back, I mean, maybe 10 years back. So with pen paper, I've written 64 bits. Then I have separated 32 bits. Then I have taken a key sequence, then passed through the fixed S boxes, what a DES has. Then 32, how to expand it, there is a rule for it. Then again, zoring it with the key. So I came up with some answer and I have cross-checked it with the book. Do I get the same response? Yes. This is how, you know, actual research start. Then I implemented that in a software called MATLAB. And that performed me all round so quickly, which initially I've done one round with pen and paper. So you can always study about DS and all. Crystal structure, block size, increasing size improves security, but slows down cipher. Key size, increasing key size improves security. True. Number of rounds, increasing will improve security, but it will increase the computation time as well, right? Because you want to encrypt some data, it will consume some time. In sub-key generation, that for the successive rounds you generate key, then round function. So all these things make the system complex, slower, but add security. So, you know, there must be a trade-off. Like I'll take example of live communication. If we want live telecast of cricket, there is, you know, picture quality is not that good because you want faster communication. But if you talk about military communication, you can't tolerate fault, but exact data. Am I speaking too fast, or that's audible and understandable? Are we good? Thank you. So, you know, so everything has a trade-off. If you have money, you have time, you can wait if the cipher is slow. You can design the complex system with putting more amount of money in it, but you don't want to compromise on security. You go with a complex, slower cipher. You want fast communication with little lower level of secrecy. Then you have to compromise on the, you know, security, because that would be a faster and less complex process. So there is a trade-off depending on what application you want it to use for. Strength of DES. See, here it is written. Brute force search looks hard. Recent advances have shown it's possible. Internet. You know, can go through the slides. In 1999, it was broken in 22 hours with the help of supercomputers. It was broken on internet in 1997 in few months. It took few months to break using brute force. 98 using this hardware in few days. When they combined these two techniques, in 22 hours, they broke DES. Now, considering alternative to DES, we have AES. AES has replaced DES, selected by NIST in 2000. So it's been 20 years we are relying on AES. Still no good block cipher has come which could replace AES. If you're looking for some improvements, you can actually study AES and work towards its improvement if you want to pursue it as your research. AES was reviewed by NSA and approved by Classical Data in 2003. It has a block size of 128. A key size could be of 128 or 192 or 256. Different versions. Rounds can be for 128-bit key, use 10 rounds, where you need lesser security, a moderate security, a very high secure system. 256-bit key and 14 rounds of, you know, algorithm, substitution, permutation, round key. Right? Same 128-bit, take an example of 128-bit input, 128-bit key, and that will be of 12 rounds, S box, P box, mixed columns. These are, you want to study in detail, you can go through. No? Passing through substitution box, using key, zoring, roll key to 4 places, and well, this is how we write functions. Rotate byte by left, 8 bits is called byte. What are stream ciphers? Apart from block ciphers, I told you, when 1 by 1 bit is encrypted. So first bit of plain text, second bit, next bit, there's ordered through key. And key here, maybe for key, we are using a pseudo-random number generator. One question, why we don't use the term random generators? Why we use pseudo-random generator?
Ma'am, you are muted. Unmute, please.
Okay, sorry, so sorry. I was mute on you. You know, nothing in this universe is random. How? You know, even if you think the stars, the galaxies, the change of season, everything repeats. You know, like day repeats, year repeats, season repeats. If you feel like that star you see to galaxy and universe, there is no repetition. If you see from other level, that will also repeat. Might be the repetition time is so long that we don't live up to that age to see the repetition. So, you know, nothing is this in this universe is random. Everything is pseudo random. So partially random. I mean, if you increase the repetition duration to such long time that you die, but before you die, you don't get to see the repetition. So we may call it pseudo random. So using the term random is not a good thing. So it has got nothing technically. It's we should use the term pseudo random every time, not random. Right? So pseudo random generators, if we generate pseudo random keys every time, it is good. So let's take some examples of stream ciphers, RC4. So I won't go into detail of this because if you actually want to pursue research in this, then you should go into detail. Otherwise, for now, just let's go through the names and little theory of it. RC4, the stream cipher, it is of variable length key. The algorithm encrypts 1 bit at a time. Stream cipher 1 bit at a time. Key is pseudo random bit generator. Output is called key stream, right? What happens? Plain text stream cipher uses XOR, exclusive OR operation, like we discussed in the beginning, right? RC4 has some weakness. It is not temper resistant. XOR of ciphertext with the same key yields XOR of the plain text. Solution is hash key with nonce, right? There are certain attacks performed on it. So I am naming some famous stream ciphers and whether they are used these days or not. Right? You can go through the slide. Then hash functions. These are very, very famous ones. What hash function does? It will convert a plain text into a fixed number of bits of ciphertext. But going back, reverse manner is not possible. A hash function is any function that can be used to map data of arbitrary size to a fixed size value. The value returned by hash functions are called as hash values, hash codes, digest, or simply hashes. So the ciphertext formed here can be called as hash value or hash code or digest or simply hashes. Properties of hash function: deterministic, means same message gives same result. My signature will always be the same. That's why bank keeps a copy of the reference of your digital signature, and every time it matches it. But they cannot reverse your signature. It is quick to compute the hash value. Infeasible to generate a message that yields a given hash value. Ciphertext to message, hash value to message, reverse direction, no going back. It is infeasible to find two different, these are certain features. Going back, no. Different messages have same hash value, impossible. Every message will have, if a new message, new hash value, right? Two different messages cannot have same hash value. Small change. So how it is used in cryptography? If somebody is doing forgery, they're trying to imitate your signature, the complete hash value will be changed, right? Because every new message will be changed to new hash value. So if somebody is trying to imitate your signature and if there is a slight difference, after hashing, it will be generated as a completely different hash. So bank has a copy of your reference, so it will be matched and caught, right? A small change to a message could change the hash value to extensively that the new hash value appears as uncorrelated with the old hash value. So reference doesn't matches here. Hash applications, security applications include message authentication codes. Authentication that I am the sender, I am sending you the check, right? Or for authentication, because authentication means sender and receiver must be the authenticated person. They can also be used as ordinary hash to index hash tables. It is used in information security. Cryptographic hash values are sometimes called as digital fingerprints, checksums, or just hash values. So you should know these terms. You should be aware of these terms. What is digital fingerprint? What is checksum? What is hash value? Diffie-Hellman keys exchange. This was a key exchange protocol. How they exchange key. This is a method of secretly exchanging cryptographic keys over a public channel and was one of the first public key protocols. How it happens? It was introduced by the name of the scientist, Whitfield Diffie and Martin Hellman. So with using their second names, we name the key exchange method as Diffie-Hellman key exchange. The protocol uses the multiplicative group of integers modulo p, where Amit asked me how public and private key there's no need to exchange. So there's a lot of mathematics involved here. You choose one random number, and modulo of this will generate some other prime number. And these are distinctive. You don't need to exchange the same key. So if you want to study, in my beginning of my research, I started studying this. This involves a lot of mathematics. For now, you get to know, you choose two random prime numbers and modulo of this will give some output, which you don't have to transfer, but the second party will use it as a decryption key. The protocol uses multiplicative group of integers modulo p, where p is prime and g is primitive root modulo p. If I start with this, now this will consume a lot of time and mathematics, which I think everybody does in interest, right? So for now, you just get to know, you really don't have to exchange the secret key. You have one key, public key, and that private key will be pair of it, and no other person can decrypt the key, right? RSA. So RSA is one of the very famous example of your asymmetric key cryptography. There were 3 scientists involved in making, these codes are not just outcome of one day. The researchers, they do research for 5, 6, 7, 8 years all together in lab, and they come up with a very good model. So RSA was the outcome of Rivers, Shamir, and Alderman, 3 scientists. One of the first public key crypto system, very famous. So RSA you should remember, and it is based on the name of these 3 scientists. It is widely used for secure data transmission because this is so good. You don't need to transfer the secret key, and your privacy, so much of secure it is. It is such a crypto system. The encryption key is public, and it is different from the decryption key, which is kept secret. This is relatively slow because here comes computation of that mathematics modulo, prime, and all, right? Bob encrypts with hello. It goes here to Alice. It encrypts with public key, but Alice decrypts it with private key. So Eve doesn't have private key, and if it reads the message, unreadable. And there was no need to exchange this private key. These are two number combinations. So good. RSA involves 4 steps: key generation, key distribution, encryption, decryption. Right? So these are mathematical functions. Message encrypted, then decrypted will give you message modulo n. So if these are all mathematics for working of RSA. I won't go into detail of that. So Elgamal encryption is also this is also an example. Like RSA is an example of public key. Elgamal is also an example of public key. That was based on modulo mathematics, prime modulo. This is based on discrete logarithm. Their mathematics inside is different. RSA was based on prime modulo. Elgamal is based on discrete logarithm. That's it. What are the big encryption trend these days? Hardware-based encryption, moving target defense, wearable two-factor authentication. Two-factor authentication, what is two-factor authentication? Even after entering the password, you get OTP. Is it a two-factor authentication? Right? You enter password, still your Gmail account doesn't open. You get OTP maybe. Or maybe in Google Photos, you have to tick, yes, I am using the device. So two-way. It is good because somebody can get to know the password, but somebody will not be having the mobile phone with the same SIM card and your phone number, right? Quantum cryptography, honey encryption, these are the trends. So if somebody, I am pursuing this. These days, what interests me is lightweight encryption. For IoT devices, which are not permanently connected to some charging points. If I want to, like we are talking to Alexa, right? We are talking to our vehicle, to our fridge these days. I want encryption there, but that encryption algorithm should not be consuming so much time, power. Then I should be using some algorithms. Those are lightweight. Do encryption, but fast, less power, less memory. So this is the hot trend. I am working on IoT improvement these days. This is my PhD research thesis topic, lightweight cryptography. Blockchains. Two of us has discussed blockchains. That was very good discussion, right? Voice biometrics, facial recognition. So these are the various branches you can pursue your studies or research. Blockchains already discussed, so I won't go into detail of that. Blockchain applications already discussed. Lightweight cryptography for IoT. This is what I am pursuing. I'm telling you, devices are talking among each other, right? So if you have some questions about lightweight cryptography, you can ask me. And with that, I'll conclude my presentation. Lightweight cryptography, you know what? Like AES is a block cipher, but AES consumes so much of memory, time, power. So if I have power constrained devices, like Bluetooth, like my smartwatch, which is connected to my mobile phone, and they're communicating. I want to encrypt some data. They run out of power very fast. So if I apply big size encryption algorithm, which will take so much of time, so much of battery power, right? So that is not good, but I want to add security. So I should be using some small algorithms. So that is lightweight cryptography is used in case of IoT. You might have heard that communicating to Alexa is not secure. FaceTime at times is not secure. Somebody might hack our data and they get to know what we are talking all the time. Alexa might copy what we are doing at home. And see, Alexa placed at some defense minister's home where all the war strategy going on. I am wearing some smartwatch and I am in some defense meeting and we are discussing something and that gets hacked. Very crucial thing, it could jeopardize the whole security system of a nation, of our government. So this is very important. So these days I'm working on it. Hopefully I'll complete my research in this. And I'll love to be in touch with you all. An important message. In theory, some cryptography functions seem extremely secure, but there are vulnerabilities. Fundamental rule you all should take from my class. Don't code your own cryptographic algorithms. Rely on AES, DES, some standard codes. Don't make your own codes. You can do a lot of research and try to improve a bit those standardized code. Don't just make your code. Because who will going to say, stamp your code? This is a very good code. How? Those codes are made public for years. Worldwide hackers try to break them. They are not able to break, then NIST says, okay, this is ISO certified. This is a good code. So don't make your own code, right? So these are the references I have used. Any doubts you have? Or we'll float some questions for you. Krishna sir, are we here?
Yes, yes, yes. Thank you, ma'am. And
Questions, MCQs, you can
nice
just try.
presentation on the cryptography from basic idea to some technical also. Here are some questions for all of you through polls. I am sharing. Ma'am, can I sharing your question through poll?
Yes, please. And this is not an exam. You can just try what you learned.
Yes. So I just launching the question through the poll regarding today's session. So just you watch and give the answer. Yes. Now
Really?
I'm sharing the question. Now there are 10 questions regarding the cryptography. This question related to the today session. So kindly read out and give the answer. Just waiting for, I think 4 minutes, sufficient, ma'am? All are getting the question? Yes or no?
There could be some questions you might not know, but that's okay. That I have not
Okay, no
covered.
problem.
You can still try.
All are getting question? Yes. Okay. 1 minute already gone. Ma'am, are you also seeing the question? Yes or no? Nilufal, ma'am?
Yes, sir.
Are you getting also see the question?
Yes, I also get to see. I am a participant here.
Okay.
So I hope everyone is getting the question.
Yes, please give the answer. There are question on the screen. Doesn't matter it's right or wrong. We just give.
We are not going to display the result anywhere. It's just for your,
Okay. I just going for ending the poll and answer also share. And ma'am, you can explain. I am sharing the answer. Okay. Now ending the poll, I think all are under doubt.
You ended the poll too early. I don't think everybody has replied to us.
I just sharing the yes.
I answered 7 only.
Okay, no problem. Now this is one by one. Ma'am, you can explain the question and give the answer. Answer also you mark here, but I think you can explain.
Okay, this is for our practice.
First question regarding the true and false. Yeah, sir.
RSA is.
Yes.
So can I?
Ma'am, you can explain.
RSA is, we just discussed, it is asymmetric. So RSA is
okay.
Used for symmetric key, false. It is asymmetric. And DES was replaced by AES. So AES is sometimes called as Rindale. Third question, exhaustive search, hit and trial. We just discussed. Oh, sir, that was too early. I mean, I am getting in the chat box that you should have given 2-3 more minutes. So you want to start the poll again or?
Again start? Okay.
I think 5 onwards they should reply back.
Okay.
I think we should give them 5 minutes.
I relaunch again. Okay, I relaunch again the poll.
Now they have the answers too. 5 answers. No problem. This is for your practice. Please try out and we give you 5 minutes.
Mohan sir, are you trying? Yes.
Yes, sir. Submitted.
Okay. Yes. I'm getting some result. Now, very nice. Now result is coming. Very nice.
So are we done with the polling?
Yes, ma'am. At least I think 2 participants give the answer. Okay, I just end the poll. No, it doesn't matter. Okay, and sharing also result also.
Let's discuss.
Yes. Now result is sharing. All are getting your result.
Okay, pretty good. So in question number 10 and question number 7, there seems to be little confusion. And question number 3. Rest all good. Okay. So question number 3, I think there should be no confusion because when we try all combination, it's brute force attack. 4th question is clear to all because image encryption is steganography. 5th question, everybody did the right. That is pretty good privacy. Sir, please scroll it down. Krishna, sir, can we please scroll it a bit?
Yes.
Yeah. What is the name of encryption decryption key known to parties? Exchange secret methods, private key. True. Please scroll it down.
Okay.
During World War II, we mentioned in Enigma one-time pad. Asymmetric cipher uses how many keys? 1 or 2? We discussed 2. 1 public key, 1 private key. Right? Original message is called as plain text. 9th question. And 10th question. An encryption algorithm transfers the message to ciphertext. True. There were 2 more questions which we couldn't give in poll. We can check here. Symmetric key cryptography, key used by the sender and the receiver is shared. Right? And cryptography, a word with Greek origins, means secret writing. So we are good, I think.
Yes,
Basics
yes,
we
yes.
got to know and everybody answered it correctly. Apart from 3 questions, there were 50-50 polling results.
Okay, thank you, ma'am, for the nice presentation for today.
Thank you, sir. So can we ask student if they have some questions, or I should write my email if they want to connect further in the chat box.
Anyone want to some question? Asking, so you can ask doubt. Thanks, Ram, ma'am.
Thank you,
enjoying
Sarah.
the session. Thank you.
Thank you, Mohan.
Okay, you can note down the email ID, our Nilufal ma'am. You can directly ask the question.
Thank you,
Shivam ma'am.
thank you, Tushari. Thank you, Priyalakshmi. Thank you, APT. If you have any questions, you can still ask. Myomin.
Thank you. Thank you very
Thank you,
much. Thank you.
Mohan. I am glad that you liked it, and I tried my best so that you don't sleep in between, because at times these sessions become so boring.
Thank you, ma'am,
Yes.
for your today's session and nice presentation.
So your voice is very low.
Yes, yes. Thank you, ma'am. Now coming. Okay. Thank you for your nice presentation for today and good expectation from participants. Also response time to time very nicely. And Mohan sir, you are excellent. I am very happy. Every day you must be some new response also and some new question also. And your response is very informative and attractive. I love you. Okay. And thank ma'am for your this time, and hopefully see you again upcoming time. And thank you all of you. See you again tomorrow. Question our here quiz session and some presentation. Anyone willing for tomorrow presentation? To please your answer, your reply give in your WhatsApp group. Okay. Thank for today joining all of you. Have a nice day. Namaste from India. Thank you, ma'am.
Thank you, sir.
Thank you. Thank you.
Thanks a lot. Thanks a lot.